Welcome to the first video in which we complete the lecture from last Tuesday. We start with a revision of the notion of recurrence time. So recall that for a state I from the state space S, the recurrence time is the time that it takes until the Markov chain starting in that state returns to this state. So for a formal definition, let tau j be the time of first passage to state j. So it's the smallest time n such that the Markov chain at that point n takes the value j. And if the chain never arrives at that state, we say that the time of first passage is infinite. Now, the probability that xn ever returns to state I then can be expressed as the probability that the time of first passage to I is finite, given that the Markov chain at time 0 starts in state I. We call that FII. Similarly, we can look at the probability that the Markov chain ever arrives at state j after starting in state I. So that is the probability that the time of first passage to state j is finite, given that the Markov chain state starts in I, and we call that Fij. So if you're interested in the probability xn returns to state I at least r times, intuitively, our notion would be that Fii, that this is Fii to the r. Because each time the Markov chain, so firstly, of course, to arrive r times, it has to return at least once, and the probability for that is Fii. Now, using the Markov property, once the Markov chain has returned, we restart it, and then again, the Markov chain has to return to the state, and the probability for that is again Fii, and we do that r times, so we get Fii to the r. Now, the slight problem is that originally the Markov property has been defined for fixed times, but here we are looking at random times. And one can easily think of examples where actually the Markov property does not hold if we apply it to arbitrary random times. However, one can show that it holds for so-called stopping times, where a stopping time is a random variable tau. So we are looking at random times. So by that, these random times are themselves random variables. And we call such a random variable tau a stopping time if the event that tau takes the value n only depends on the realization of the underlying Markov chain up to time n, so on the values of x0 up to xn. So the notion of stopping time, the name can be thought of that we want to stop the Markov chain, and our decision to stop, so to set tau equals n, must only use information available at that point in time. So it must only use any information provided by x0 up to xn, but must not use any future values. Our time of first passage, tau I, is a stopping time because we can express the event that tau I equals n in terms of the underlying Markov chain by noting that it's equal to x1 being non-equal to I up to xn minus, so the Markov chain at time n minus 1 being non-equal to I, but at time n, the Markov chain takes exactly for the first time the value I. As I already mentioned, we then have the strong Markov property. So for any stopping time tau, the probability that the Markov chain at the stopping time +1, so the next time after the stopping time, takes the value j. given that at the stopping time it takes the value I, provided the stopping time is finite, is exactly the transition probability from state I to state J. So this is a Markov property because it cancels out any dependence on the past that might be inside this conditioning on the stopping time. So because that's a random time, it might of course rely, as we already here see, rely on the past, but this actually is of no relevance for this transition here, and the probability of this transition is the same as for any fixed time. And with that, we can now use the strong Markov property to find that if we have tau IR being the time at which the Markov chain returns for the last time to the state I, so we're interested in the probability that tau IR is finite, provided that tau IR minus 1 is finite, so the chain already has returned R minus 1 times. And the question is, does it return another time? What is the probability for that? Now, we have here, then we can rewrite that as the probability that tau IR is finite, given that x tau IR minus 1 equals I. So because we know that at the stopping time, our Markov chain takes the value I, we can plug that in here. This is already contained here in this information that that is finite. And then we exactly have here the conditioning set that we have here for the time tau IR minus 1. So now we are indeed looking by the way of strong Markov property just to the probability to return yet another time, and the probability for that is FII. Okay, and then of course by iteration we can write the probability that Ri is larger equal to R, provided we start in I exactly as FII to the R. More extended proof you can find here on that slide. I don't want to go through that here. Now, an important consequence of this result is that as we let R tend to infinity, so the question, what is the probability that the Markov chain returns infinitely many times to the state I, that this either takes the value I, namely if FII equals 1, or it takes the value 0, namely if FII is smaller than 1. So that means that either with probability 1, the state is visited again and again, or after finitely many times, it is not visited again. So in the long run, these states of the second kind do not play a role. They become forgotten, and the Markov chain completely concentrates on states of the first kind. So because of this very different behavior, we call the states of the first kind recurrent. So recurrent state is recurrent if the Markov chain returns to the state infinitely often with probability 1. Or it is called, state is called transient, second kind, if the Markov chain returns to the state only finitely often with probability 1. So this theorem repeats the definition here and gives another characterization, namely that the sum of the n-step transition probabilities summed over all possible steps n is either finite in the recurrent, infinite in the recurrent situation, or finite in the transient situation. A proof of this fact is given here. Again, I don't want to go into detail as this is of secondary interest. Now we have looked at the recurrence time, that is a random variable. So we can also look at the mean of this random variable provided it exists. So how long does it take on average to return to a state I? So the first passage time tau I gives the time of first return to state I if the chain started in the state I. So the mean recurrence time, which we call mu I, is the expectation of the first passage time to I, given that the Markov chain starts in that state I. And that can be expressed as it's an expectation. So we are looking at the probabilities that tau I takes the value n and multiply this by the outcome n. So that is the ordinary definition of an expectation. And these here are called FIIN, the probability that the chain returns to the state I after exactly n steps without visiting it in between. Now, as for a transient state, the probability that the chain does not return to the state, so the which equals is identical to the recurrence time taking the value infinite, as this has a positive probability, the mean recurrence time must be infinite. Okay, because there is a chance that we do not return. So in an average, this automatically puts the average to infinite. So on the other hand, if we now look at recurrence times, so let's copy paste mistake, that should be here. If we look at the mean recurrence time for recurrent states, then we definitely have that the probability that that tau I is finite, so that the chain returns, equals 1. So the chain returns with probability 1, but this does not necessarily imply that the mean exists, so the mean is finite. We know that random variables can have a valid distribution, but need not have an expectation. So that means we only have a mean if the probability to take large values becomes small fast enough. So because of that, we make another distinction. Namely, we say that the state I is positive recurrent if the mean recurrence time takes a finite value, so is finite, which implies also recurrence. It can no longer be transient because all for the mean recurrence time, of course, is anyway infinite. And secondly, we say that a state I is null recurrent if it is recurrent, so the probability that the recurrence time is finite equals 1, but the mean recurrence time is still infinite. So that means even so the chain returns with probability 1 again and again infinitely often, the times between the coming back can be arbitrarily long with too large probability for the mean to exist. Okay. So now I come back to what I already said in the tutorial. So we can now classify states according to recurrent and transient. And for that, we can utilize our graphical description. So first, we say that a state J is accessible from state I if the probability, there is an n-step transition probability from I to J that is positive. So it is possible to go in n steps from I to J with a positive probability. And I and J communicate if J is accessible from I and vice versa. So there are multi-step probabilities from I to J and from J to I that are positive. Graphically, that means that J is accessible from I if we have a path in the graph from I to J. So next we say that I and J communicate, and we write it as here, I left right arrow J. Then by definition, as we also look here at transitions of step size 0, where the transition matrix, of course, is the identity matrix. So we have necessarily I communicates with I. Then it's, of course, a symmetric notion. So I communicates with J and J communicates with I. And finally, we have this transition property that I communicates with K and K communicates with J. Then I communicates with J. And we can simply see that if you have a path from I to K and a path from K to J, then of course we also have a path from I to J and vice versa for a path from J to I. So I and J communicate. Now, next, let Ci be the set of all states that communicate with state I. Then if we look at two different states I and J, their classes are either identical or disjoint. If the two sets had a non-empty overlap, so their intersection is non-empty, then we have a set element K in that intersection that communicates with I and it communicates with J. And then by this property, we already see that I and J also must communicate and therefore must be in the same class. So as soon as the two sets have a non-empty intersection, they must be actually identical. And by that, these classes here actually form a partition of the state space. So all sets are disjoint and they cover the whole sample space. We call something like that a partition. As an example, here we have a transition matrix of a Markov chain with 7 states. And here we have the corresponding graph. And now we can see for the classes. First class would be 1 and 5 here, which clearly communicate with each other, but do not communicate with any other of the states. 1 is accessible from 2, but not vice versa, for instance. Next, 2 is a class in itself, because there are only outgoing errors, but no incoming error. So we can only leave the state and never come back. So it is a class in its own. Same for 3, we have 1 incoming edge and 1 outcoming edge, but there's no way back from 4 to 2. So 3 again is in itself a class. And finally, we have here, because of this loop, the final 3 states form a class. They are all accessible from each other, but they're different from the other classes. Now, the classes become important because the main properties that we have for a Markov chains are actually class properties. So, for instance, if a state I is recurrent and it communicates with another state J, then J is also recurrent. And we can simply see that if I and J communicate with each other, then there exist two k and n step transition probabilities such that the transition from J to I in k steps has a positive probability, and the transition from I to J in n steps has a positive probability. Then we can see that by the Chapman-Kolmogorov equation, that the probability to start in J and return in J in k plus n steps can be lower bounded, because Chapman-Kolmogorov, this would be a sum over all intermediate states. We only pick here this particular element where the intermediate states are actually the state I. So we have a transition from J to I, then a loop from I to I back in m steps, and another transition from I to J in n steps. In total, again, k plus n steps. And because all the other paths that are possible only increase the probability, this is the lower bound for this probability. And then we can simply note that by the one result that I briefly gave, I is recurrent if the sum of all these m-step transition probabilities is infinite. So if I sum here over m, this part here, I get infinity. And now if we simply take here the sum over m, then as these do not depend on m, we have this factor times the sum over all m of this part times this factor. And as this is infinite, we get as a lower bound infinity. And by that, the sum over all m of this probability must be also infinity. And therefore, state J is recurrent. So as we have classes, one element in there recurrent, all elements are recurrent. That also implies that if there is one transient state, no other element can be recurrent. So a class is either fully recurrent or fully transient. Recurrence and transience are both class properties. So how can we determine whether a class is recurrent or transient? So for this, we look at the notion of a closed class. A closed class is a class which cannot be left. So the transition probability is Pij for I being inside the class and J being outside the class are all 0. So the class cannot be left. There's no transition out. So graphically, such a class has no outgoing, but only possibly incoming errors. And every recurrent class must be closed, because otherwise we could leave it and never return back, which, as we already have seen, then would imply transience. So every recurrent class is closed. Vice versa, however, not every closed class is necessarily recurrent, but only every finite closed class is necessarily recurrent. So this is a more mathematical idea of showing that every recurrent class is closed. So we know that this probability here equals 1 for a recurrent class. And it is upper bounded by 1 minus Pij, where the Pij is a transition from a state I to a state J outside the class. And if this equals 1, so if we assume recurrence, then this implies that Pij must be 0, because otherwise we would have here a smaller value than 1, which would violate this inequality. So Pij by that must be 0 for all j outside the class. And for the second result, if we only have finitely many states, each after finitely many steps is not anymore visited with probability 1, then altogether after finitely many steps, any of the finitely many states in the class would not be visited again, but that would of course violate the notion of closedness, and therefore we cannot have any transient state inside a finite closed class. And by that it must be recurrent. As an example, that is the example from before, we have 4 classes. Clearly, this class here has no outgoing edge, so it must be recurrent. This class here has outgoing edges, so it must be transient. This here has an incoming, but also an outgoing edge, so again, it's transient. And finally, if this class has no outgoing edges, so it is again recurrent. So that is exactly this result. Then next, we looked at the periodicity. So the period of a state is the largest number d, such that the n-step transition probabilities for a transition from state I back to state I are 0 whenever the step size n is not divisible by d. So that means vice versa. If the chain returns to state I, it's only possible at multiples of the period d, but it's not bounded to have a positive probability to return at every multiple. And the important part is we look for the largest such number d, such that this holds here. If d equals 1, we do not call the period 1, but we call that aperiodic. In the graph, this means if a state has period d, then every path from I to I is of length nd, so its length is a multiple of the period d. And then this implies that in a class, all states must have the same period. So periodicity again is a class property. Then if we have an element that has in the graph a self loop, or it has simply a positive probability for the Markov chain remaining in that state, so the transition from I to I has a positive probability, then the class is aperiodic because the chain can return to the state in one step. So for proof of the periodicity, and the idea is simply that we have 2 states I and j in the same class, and suppose they have periodicities d and t prime, then because they're in the same class, there exists a transition from I to j, say in m steps, and there's a possible transition from j to I in n steps. Now, because if we put those 2 paths together, either way, we either get a path from I to I or from j to j. So m plus n must be divisible by both periods d and d prime. So that means that m plus n is a multiple of d and a multiple of d prime. Now, if we look at any r, so all the possible transitions from I to I, say the corresponding path has a length r, then r must be a multiple of d, because d is the periodicity of I. Now we can look at j and construct a path from j to j, namely by first going to I, then using this path here, and then going back. So by that, we find that n plus m plus r, which is the length of this path, must be also a multiple of d, prime, because now the d prime is the multiplicity, is the periodicity of j. So that is this here. On the other hand, r is so n plus m is a multiple of d prime. So we have this here. And by that, r must also be a multiple of d prime. So r is divisible by d prime. D was the largest common divisor, so that is, we choose d as large as possible. And therefore, d prime must be smaller equal d. Now we can reverse the picture, so we exchange the roles of I and j. Otherwise, same picture, and we find then similarly that d is smaller equal d prime, and therefore d must be equal to d prime, so the two periodicities must be the same. So in our final slide, we have a few definitions. A Markov chain is called irreducible if its state space consists of a single class. So all states communicate with each other. So reducibility means that we can split the Markov chain in classes. Each class kind of forms a superstate where the chain remains for some time, and then if it's a transient class, it leaves it after some time. So it's a more abstract pattern looking how the Markov chain moves between classes, and we have irreducibility if there's only one class and it cannot be split up in these superstates. A Markov chain with finite state space is called regular if there exists some n such that the n-step transition from I to j has a positive probability for all possible states I and j. So the n-step transition matrix has only positive entries. In the tutorial, I falsely called that ergodicity. Actually, it's regularity. Ergodicity, on the other hand, means that the Markov chain is irreducible and positive recurrent. In particular, if we have a finite state space, irreducibility is the same as ergodicity. But if we have infinite number of states, class of infinite size actually could be transient, even so there it's the only class, so the Markov chain is irreducible. Same, we can have the difference between null recurrence and positive recurrence. Ergodicity we only have if we have positive recurrence. I come back to this notion later, but otherwise will not use it much, as there is some confusion in the literature about when a Markov chain is ergodic. regularity we need for the assignment. And irreducible, however, is a very important notion, because that means that, for instance, if we have a finite class, finite state space, we only have one recurrent class, so that limits the possibilities. We immediately know that in the long run, every state is of importance, which is very important to know. That completes the first lecture, and I hope that it gave you valuable information. Thank you.